yeah, and nebulae can come in all different shapes and sizes. So for the most part, they're, you know, hundreds of light years across. They can form a bunch of stars, and any leftover gas that doesn't end up forming stars will form asteroids and comets and new little baby planets to orbit their, you know, new baby star friends. The Trifid Nebula is actually up. Trifid's hanging out in the sky tonight. I always love when I give talks on these things, and something that I really like is like actually up and you could like see it later. Now the Trifid Nebula is a really interesting nebula because we see, you know, these stars in the center here. They're like these really bright blue stars. They're protostars, so they're like baby stars. In space, if something's like blue, or if a star is blue, we kind of saw on the HR diagram. It's normally a lot hotter, and it's a lot younger. So young hot stars appear to be more blue or white. Older stars appear to be more yellow, orange, and red, and they're actually cooling down. So these stars, these orange stars that we're seeing, are not in that nebula. They're, you know, kind of in front of it, or they could be behind it. Yeah, when a star, you know, a hotter star, hot is blue in space and cold is red in space. So it's kind of flipped around there. So I also like to mention, I've been showing, you know, cool pictures of nebulae. Astronomers lie. Now, I'm not an astronomer, so I'm not lying to you. But what I mean by that is, you know, we see all of these, you know, if you're a nerd like me and you've looked up like cool space photo on Google before, which I do literally every day, you'll see these really insane, like really cool, like gaseous regions, all of this really cool light and stars and galaxies. Astronomers, you know, they can use instruments and special tools on telescopes that help them see in wavelengths of light that we can't see with our human eyes. So if we were to look at the Orion Nebula, we saw that video of it earlier, and all three of these images here on this slide are the Orion Nebula, just with different effects or wavelengths of light. You know, yeah, so astronomers can cheat, and they can see in different wavelengths of light. So if we were to go and look through a telescope and look at the Orion Nebula, he's not in the sky tonight. He set about a month ago. He sets pretty early now. Through a telescope, what you'd see is pretty much like that center image there, that bottom image. So you'd see some blue gas, you'd see the bright blue baby stars, this little group of like 4 stars in the center there, that's called the trapezium. You'd see a dark nebula, so kind of like this darker region, which looks like, it kind of looks like nothing's there. That gas is just so dense and in front of the light source, so it looks like it's backlit. So yeah, if you were to look through a telescope, look at the Orion Nebula, you'd see this, which is fascinating. And in the top left over here, it looks like they took like a 15-second exposure and just cranked that hue all the way to like the blue pink end when editing. So doesn't really look like that. And this image off to the right here, still the Orion Nebula, but they're using, again, non-visible wavelengths of light. So like if we were to take all of these wavelengths of light, so there's, you know, gamma and X-ray and ultraviolet and visible and infrared and radio and microwave, all of this whole, all the E&M spectrum, the electromagnetic spectrum, for to put all of that light and put it on a meter stick. Every single color you've ever seen, every single shade of anything on this whole spectrum, every color you could imagine is worth like the width of a hair, like every single color you've ever seen. So there's all of this stuff that we can't see because we're just humans, and but we do have the technology to see these wavelengths of light. Also, human eyes, we forget what we see every second. I wish we could stack images. That'd be so fun. But what I mean here is, you know, as we look at the Orion Nebula down there, it's not going to just start getting brighter every second as we look at it more. But with an image over here, we'll have cameras open to the night sky for minutes or hours or days to collect a ton of light, to collect all of these cool details, as well as collecting like infrared light and X-ray light or ultraviolet light. And then we're able to compile all these images together. So some photo editing goes on when we see these images. So basically, what I'm trying to say here is all of these images are cool. They're all really neat. It's all, really, really cool science. What the Orion Nebula is. It's, a stellar nursery, but it can, look super different depending on how you are looking at it. Now, once these stars are formed in this nebula, in this cloud of gas, a bunch of different stuff can happen. We can get like families of stars. So this guy right here, this system, it's called a binary system. This is Albireo, which is actually the head of Cygnus the Swan, the constellation Cygnus in the night sky. Cygnus is rising right now, so he'll be visible. In Arizona time, he's visible around like 10 p.m. So if y'all happen to be out and about later on, he'll be hanging out. Now, binaries are really interesting because when you look at this star with your naked eye, just like looking up in the night sky, it looks like a single star. But through telescope aid, it's actually two stars orbiting each other. And binaries are neat as well because over half of the stars that we can see in our night sky, those 2,000 stars that we're able to see, over half of those are actually binaries. We just can't see them with our naked eye. But again, through telescope aid, it's actually, we can see it's a little family, two guys hanging out. So how binaries work is, these two objects, these two stars, they're going to orbit the center of mass. So we call that the barycenter. So if two objects are the same mass, that barycenter is going to be right in the center, right in the middle of these two objects. So they're going to, orbit around pretty evenly. If one object is a little larger, that barycenter will be closer to the larger object. So that guy might stay a little more stationary as the smaller object is orbiting around it. Now, if we get more stars that are, that form really close together, we can get larger families of stars. We can get what's called an open star cluster. So this open star cluster specifically is really neat. It's kind of rare to see something like this. So you see there's kind of like two denser families of stars. What we think happened was, there could have been like a giant molecular cloud, so a giant nebula, and that nebula might have broken up, and then all of these stars formed pretty close together. But it's called an open star cluster because these stars didn't form a strong enough gravitational pull to like stay together or stay orbiting each other. So they're slowly drifting apart from each other. And that's why they're called open clusters, because it's like they're opening up. So yeah, the Perseus double cluster is not in the sky right now, but yeah, open star clusters are super common. We normally have a lot in the sky, any given night, any time of the year. And we can also tell that for the most part, these guys are younger stars, again, because they're more white-blue colored, so they're hotter, younger stars. So open star clusters don't last a long time. The stars will last a long time, but the clusters themselves, since they're drifting apart, you won't see like red stars or older stars be a part of a open cluster. So these red stars that we're seeing, they're most likely, in front of the cluster or behind the cluster. Now we can just keep going here. So if there's just a giant nebula, and instead of forming dozens or tens or dozens or hundreds of thousands, a nebula could form hundreds of thousands of stars and glob them all together. So M13 is in the sky. He's the Hercules cluster. So it's kind of in like the armpit of Hercules almost in the sky. And we can't see any of this with our naked eye. A globular star cluster is a giant like family of stars. So globs will have hundreds of thousands of stars, all strongly gravitationally bound to each other. So these guys, there's some center of mass. There could just be a bunch of stars real close together that makes the center the center of mass, or there could be a small black hole, like a stellar massed black hole in the core there. Some people think globs are dead galaxies that like things like the Milky Way or galaxies like ours have sucked up, and they're hanging out on the outskirts of our galaxy. They're normally found on the outskirts of galaxies like ours. So this guy, the Hercules cluster, we've got, again, hundreds of thousands of stars. And I love that scientists came up with a very sciencey science term of glob, because we call them globs. All of these stars are globbed together and they're stuck and they're just orbiting around each other while that whole glob goes around our entire galaxy. I love looking at these guys through telescopes because specifically because of like what kids say they look like. Because all the time kids will be like, oh, you know, it looks like a dandelion or firework or dewdrops in a spider web. One of my favorites was, oh, it looks like unicorn snot. And I was like, wow, that will stick with me for years. And it has. So now every time I see a glob, I'm like, yep, that's what unicorn snot looks like. This guy is around 20, 30,000 light years away. Now, I've been saying, you know, like light years, you know, light years in tens and thousands and hundreds of thousands, you know, light years away. That's a big number. And how I like to explain light years is a light year is the distance that light travels in a year. So a little piece of light, a little photon, a little light particle, zooming through space for a year, that distance that light traveled is 6 trillion miles. So a light year is 6 trillion miles. Now, trillion is a big number, and I've been saying, you know, millions and hundreds of thousands. A trillion, yeah. So how I like to explain how giant a trillion is if we were to count to a single million, a very, very, very small fraction of a light year, like, you know, the right way, 1, 1,000, 2, 1,000, you know, kids will always be like, well, I can do it right now. Watch 1, 2, 3, 5. And it's like, no. If you like every second, a million seconds will be about 11 days. So yeah, a million seconds around 11 days. If we were to count to a billion, so again, very small fraction of a light year, that would take you about 32 years. And if you were to count to a trillion, 1/6 of a light year, that would take you 32,000 years. So a trillion is a big number, and a light year is a very big distance. So yeah, this guy around 25,000 light years away from us. That's also crazy to think about, because if you're looking at something that's however many light years away, if you're looking at something that's 4 light years away, that light took 4 years to get to your eyeballs, which means you are looking in the past 4 years. So by looking at this guy, 25,000 light years away, we are looking 25,000 years into the past. By looking at galaxies that are 2 million light years away, we're looking 2 million years into the past. So I like to, you know, astronomers are basically like time travelers, you know, for a living. Now, this is actually one of my favorite like size comparison videos. I think it was trending on Facebook like years ago. You may have seen it around, but this is an accurate representation of how large the planets are compared to stars, and how large stars are compared to the planets. To put that in perspective, we could fit about 1 million Earths inside of our sun. And we're just going to keep going. You'll notice for the most part, I think there are a few outliers, but normally as a star gets larger and larger, it'll appear to get redder and redder. Again, I think Rigel and then like a Pistol star are like the weird outliers there. And we're still going. Antares is actually one of my favorite stars, and I'll explain exactly why in a second. But we hit VY Canis Majoris, and VY Canis Majoris is now no longer the largest known star. I think we found a few, or at least one, that's larger. We'll zoom right on in to our tiny little house. So VY Canis Majoris is so ginormous. If we were to take like a standard like Boeing 747 and fly it around VY Canis Majoris, it would take about 1,200 years just to make like one rotation around the entire star. Now, Antares is my favorite star because the naming of it is so dumb. It's not dumb. I think it's just funny. Because in our night sky, way back when, ancient astronomers noticed that there's kind of like one common path in the sky that planets take. And that's now called the ecliptic. So old astronomers were looking along this ecliptic and they're like, okay, that's Jupiter. Over there is Mars, that red dot in the sky. But wait, there's another red dot in the sky. Wait, hold on. Is that one Mars or is that one Mars? Okay, no, that one is Mars. That one is not Mars. So Antares translates to literally not Mars. And when it's in the sky, like it's in the sky tonight, haha, Antares and Mars are both in the sky. He looks a lot like Mars. Red stars will appear red in the sky, and blue stars appear pretty like white or blue in the sky. One like a way you can tell the difference between planets and stars, though, is planets in the night sky don't twinkle, and stars do. So if I think actually right as the sun sets, you may see some really, really bright thing over on the western horizon, and it's not twinkling, and that's Venus. So Venus is hanging out, Mercury's hanging out. Venus is known as our morning or evening star, but you'll usually see it like near our horizons just as the sun rises or just as the sun sets. So the like lives of stars, again, we're basically professionals at this point. They start from these giant molecular clouds called nebulae. And the kind of like when you get to the middle age portion, or like the I guess the middle of a life of a star, you kind of hit the same thing. That star is burning its hydrogen fuel for billions of years, and then we may run out of hydrogen fuel. So at that point in time, that's kind of what sets off this star becoming a red giant or red supergiant. So when a star runs out of fuel, it will start fusing the elements that it's already created. So it'll start fusing helium atoms into other things, and we'll get some like light metals out of while stars are fusing. The heavier the star is initially, the more massive the star is initially when it was first like created, the heavier the death, I suppose, the more massive that star can get as it's fusing more and more and more elements. So a normal, smaller average mass star, it'll turn into a red giant, and then we'll hit what's called a planetary nebula. And I'll explain exactly what that is in a second. Again, the heavier the star, the heavier the death. So if we have a giant star in the beginning, it'll hit a red supergiant, and then we get a heavier explosion, a heavier stellar death called a supernova. Now, with a planetary, or as a star like gets larger, or as a star ages, I was mentioning that it gets larger, but exactly how large is it getting? I mentioned earlier, I explained light years. Now in our solar system, normally we don't use like miles. I just use them because I'm in the United States and we're too stubborn to switch over to kilometers, but most of the world uses kilometers or AU. So 1 AU is 1 astronomical unit. 1 AU is 1 Earth to sun distance. So 193 million mile distance. So like Pluto is around like 40 AU away from the sun or something like that. So once our sun hits its red giant phase, it will start kind of bubbling up, kind of having a little tummy ache, a little bloat, if you will, and it will completely engulf Mercury and Venus and Earth and Mars. So that's going to be one big boy. We can see here the sun is a red giant, the diameter 2 AU. Right now, the diameter is 0.01 AU. Mars is about like 1.5 AU away from the sun. So Mars is a goner, Earth's a goner. But again, we've got around like 5 billion years, maybe a little less than that, before something like this happens. So, mark it on your calendars. Now, with the death of an average mass star, a lighter mass star, we'll get a planetary nebula. So with a planetary nebula, it's called a planetary nebula, but there's no actual planets involved. It's just when we were first like cataloging deep sky objects, some guy was like, this little thing in the center looks like a planet. And then there's gas over here going around the whole thing. So gas in Latin is nebula. And then here in the center looks like a planet. So planetary nebula. We now know that that's not a planet. That's actually the dying core of the star. And that dying core is expelling out all of the gases and elements that star has created throughout its lifetime. So since it's a lighter massed star, we're getting lighter gases like nitrogen and oxygen and helium. And those different colors represent like different gases. And the normally nebulae or planetary nebulae will be around like a light year across in diameter. So if there's any planets in there, those got burnt up when that star either got really big or when that star exploded. Now, again, the heavier the star, the heavier the death. So a supernova is like the death of a more massive star, so we'll get more like heavier metals and heavier elements with a supernova. So if you're wearing like a gold ring or gold jewelry, that gold was formed from within a supernova. And this guy, or this supernova, the Crab Nebula, is interesting because it actually exploded. This star died back in like the 1000s, like 1050 AD, something like that. And it was like written down, like cataloged by ancient astronomers, like the sky is falling and the world is ending. So they could see that on Earth, this star that's thousands of light years away dying. The Earth didn't end. It was just like a really cool light show. And this remnant is still visible today. That star that died thousands of years ago, so we can still see it. Now, the next star that's set to go supernova in our night sky that we will be able to see is Betelgeuse. So Betelgeuse is the shoulder of Orion. I've already said it twice, so I can't say it again. But this star is around 600 light years away. So, you know, by looking at this star, we're looking 600 years into the past. When this star does go off, which could be like tonight or like tomorrow or 10,000 years, which is relatively soon in astronomical terms, when the star goes off, it will be the size and luminosity of a full moon. So like, you know, you can see the moon during the day. We will be able to see this star die in the middle of the day if it goes off in the middle of the day, wherever you are on Earth, for 2 weeks straight, the size and luminosity of a full moon. And it won't harm us in any way since it's so far away. But it's crazy to think about that star could have exploded 599 years ago, and we won't know till next year. Now, if Betelgeuse, I said it 3 times, oh well, were to be in the center of our solar system, it would engulf our entire sun, Mercury, Venus, Earth, Mars, the entire asteroid belt, and Jupiter. So this guy is like a big old boy. He's a big old star. We can see there, size of Jupiter's orbit. So that'll be fun. That'd be kind of cool to see. We'll always take like bets at Lowell, like, you know, I think it's going to go off this Valentine's Day, and then it didn't, but maybe it did, but we won't know for 500 years, 600 years. So we'll see. Now, this image was actually taken by, or this was taken in X-ray. So the X-ray wavelength of light instead of like infrared or ultraviolet or visible, or it's taken in visible and X-ray. So really energetic particles. This star is a pulsar. So we can see some like stuff kind of going, some weird light hanging out in here. And it's not like a noticeable star when you're looking at it with your naked eye. So it doesn't have a cool name. It's like PSR, blah, blah, blah. But I mentioned binary stars earlier and how over half the stars in our night sky that we see are binaries. So if there was a supermassive star that went supernova and it was part of a binary, there's stuff could happen. So one of those things is we could get a pulsar where that star explodes, that massive star explodes, and that little partner that it had just spins out uncontrollably, ejecting a bunch of light and mass from its poles. So it looks like it's pulsing, or like it's like flashing, like little, like really quickly spinning lighthouses out in space. We've actually seen pulsars that have spun 43,000 times per minute. So that's a crazy, you know, how powerful these explosions are. Another outcome, if a binary star in a binary goes into supernova and the other guy doesn't, is we'll get a neutron star where that star will kind of sort of collapse in. So that star neutron stars are like the size of a city, so like the size of New York, but the gravity 2 billion times that of Earth. So this really dense little dude out in space is a neutron star. So yeah, pulsars, neutron stars, supernovae, planetary nebulae. Oh my, we're rocking through this. Now, of course, everyone loves these guys. So if a star is so incredibly massive, so ginormous, when a super giant, an incredibly super duper super giant star dies, it'll try to explode, and it actually ends up collapsing in on itself, making a rip in space-time. And this rip in space-time has mass and nearly infinite gravity, and that's what a black hole is. So a lot of people have heard before that, like, oh, you know, black holes, they're big planet eaters and star eaters, and they eat everything in their path. They're mostly like gravitational bullies. So over on the right, we can see, you know, over the course of like a decade or so, we're actually watching stellar movement in the center of a galaxy, and we see these stars are just kind of being like flung around this point that we can't see any light being emitted from, and we believe that that point is a supermassive black hole. So we can see, so that black hole is kind of acting like a gravitational slingshot as these stars are going around. It's just being thrown out of its original orbit. The gravity of a black hole is so insane that over in these images here, we can see, we'll get an effect called gravitational lensing. And so that gravity is so strong that it bends the light around the black hole. So like here, you know, this galaxy here doesn't normally look like that. That's like a galaxy where we'll see more of like a linear shape, but there's some black hole in there. So like where we are on Earth and where that galaxy is and wherever that black hole is, that gravity is so strong that it's just bending the light of that galaxy. So that galaxy doesn't actually look like that. It's just where we are in the universe makes those galaxies look like that. This is one of my favorite pictures of gravitational lensing, because the gravity is lensed in such a way, or the galaxies are lensed in such a way that you see a little smiley face, like a stupid little smiley face with his little head and his mouth, his two eyeballs, his nose. I love that. Now, you may have seen, I think it was about 2 years ago, we got the first ever image of a black hole. Now, I did not think something like this could happen in my lifetime. And this was giant news. And, you know, you may have seen this before and thought, like, it looks like a cat eye, like what's so special? This area of space, this was taken from the center of a galaxy that's about 50 million light years away. And the area of sky that we're taking an image of is the size of like an orange on the surface of the moon. So this like itty bitty little spot, and we are able to see a black hole. And it's crazy because like Einstein and Hawking, they had these predictions of like how a black hole worked. Because if, you know, 3 years ago, if you looked up a picture of a black hole, you saw like a black sphere and some light kind of going around it. So it's like, okay, there's the body of a black hole and the accretion disk, but we never saw a picture of one. That was just math and physics told us that's what black holes looked like. And then we got a picture of a black hole, and that's exactly what a black hole looks like, which is fascinating. Like physics is so cool. So what's going on here is we have this point of nearly infinite gravity. And as these stars are going around this black hole, sometimes that black hole will, you know, take a little bite out of a star, not, you know, engulf the whole thing, at least not all of the time. So it'll rip some mass, rip some mass, rip some light off of that star. And it'll kind of throw it around the black hole into what's called an accretion disk. So that's that accretion disk, a bunch of star guts going around a black hole. And how we took a picture of this black hole, we took an Earth-sized telescope called the Event Horizon Telescope. And when I mean Earth-sized telescope, I mean a bunch of telescopes, a bunch of arrays across the entire world. And we aimed all of these scopes at this little orange on the moon sized spot in the sky. And we got a picture of a black hole. Now, when I talk about like the gravity of a black hole, it's weird because I keep saying like they're massive. They have almost infinite gravity. You may have heard of like the bowling ball and the blanket analogy. If you have no idea what I'm talking about, hear me out. So if you were to take a blanket and, you know, hold it up at all four corners, so it's just like a line, and put a bowling ball in it, that bowling ball is going to dip. So the blanket is like space-time, and that bowling ball was like our sun. So that dip in the blanket is the sun's gravity, you know, all of the power that the sun's gravity has. A neutron star is a little more powerful, so there's going to be a heavier dip. And with a black hole, it's like if I were to somehow poke a hole in the bottom of the blanket where the bowling ball is, and now the blanket falls infinitely through the hole. That is the gravity of a black hole, which is really weird to think about. And it's also even more crazy to think about because, like, that's what we think is going on. Like, we've never been into a black hole before, but you know, we predicted what one looked like through physics, and we found out that that's what it looked like. And this, you know, the anatomy of a black hole. I actually love what was it? I think it was Interstellar, the movie Interstellar. Where Matthew McConaughey, oh, this might be spoilers, I'm sorry, he jumps into a black hole and he's like, I'm approaching the event horizon. And when I saw the movie and I heard him say that, I was like, that's exactly what you are approaching, Matthew. Good job. Because the first part of a black hole is like the event horizon. So like if I were to jump into a black hole feet first and pass the event horizon, that's like the point of no return. Like once you pass the event horizon, you are Dunyan rings. You would have to travel faster than light speed to escape it. And that is currently impossible. So yeah, that's it. So as I'm falling through the black hole, I've passed the event horizon and I'm approaching the singularity, that rip in space-time, that point of infinite gravity. I'm going to experience more gravity at my feet than I will at my head. So my body is actually going to start stretching out and ripping apart and stretching out more. And then the atoms that make up my body are going to rip apart. And then the quarks and leptons that make up my body are going to rip apart. And then we get into quantum mechanics and no one cares. But that whole process is a real sciencey science term called spaghettification. And I love that. Glob and spaghettification are some of my favorite terms that I get to say. So once I'm ripped apart and I hit the singularity, we have no idea what happens. No idea. There's all of these theories that say like, oh, you can time travel if you jump into a black hole, or black holes are wormholes to another galaxies, or all this stuff. We have no idea. It's fun to think about for sure, but I've never done it, and I don't think any of you have. And we haven't chucked anything into a black hole yet, so it'd be cool if we could, but probably wouldn't really survive the fall in there. So maybe we'll figure something out soon. Maybe we will. All right, here. I didn't think we'd get a picture of a black hole, so we won't figure out what's how black holes work in my lifetime, and then I'll jinx it. Now we'll figure it out. So black holes are very common. There are stellar mass black holes, so smaller black holes that are hanging out like in galaxies. There are also supermassive black holes, and these guys are in the cores of galaxies. So normally when you close your eyes and think of a galaxy, you're probably thinking of a spiral galaxy. So like this guy over here, we have the core of the galaxy, we have the spiral arms going out here. Spiral galaxies are normally like middle-aged or younger galaxies. We know this because there's still a bunch of star formation happening. We can see this with the arms and the brightness in the arms, the gases in the arms. So we know like a galaxy is young or middle-aged because there's still a bunch of stuff going on. Now, also this galaxy here, the spiral galaxy is called the Whirlpool Galaxy, or M51. And the Whirlpool is one of my favorites because, again, a wonderful term that I get to say for my job. We see galactic cannibalism here. So this guy is literally eating this guy over here. We can see like the arms kind of going around, and he's just munching on all the light that we see in there. But this guy is still kind of putting up a fight because we can see the spiral arm going around here, and the other spiral arm, it's kind of bent right there. So this tiny, weird, irregular galaxy is pulling on this guy's arm. Irregular galaxies, they're really funky, and a lot of astronomers are studying them right now because we can see star forming happening, but we don't see like a core of a galaxy, or yeah, there's dwarf galaxies, regular galaxies. We don't know exactly what's going on with them, so they're still like a hot topic to study. Now, elliptical galaxies, they just look like a little smudge or like a giant globular cluster. Ellipticals have used up all of the gas in their galaxy, so all of those stars are, or there's no more baby stars being born. So there's no spirals. We just see this giant cluster of stars. Like hundreds of billions of stars instead of just a couple 100,000 like what we'd see in a globular star cluster. Now, yeah, irregular galaxies they vary all over the place. Now, our own galaxy, we believe it's a spiral galaxy, just by looking out and being able to map, because we are inside of our own Milky Way. So we can't really get a picture of it. So this is an artist's rendition. But our Milky Way is about 100,000 light years across. So this gravity of our supermassive black hole in our center there, Sagittarius A, which we are 22,000 light years away from, which is a perfect distance, that gravity is felt 50,000 light years in every direction. And that's great. That's keeping us together. It's wild to think about because our galaxy has 400 billion stars in it. And, we can see about 2,000 a night, which means we see barely, like 0.000000000%, 2% of the stars in our galaxy, which is crazy. Space is giant. I love that. Now, if we're to keep zooming out, so this is about a 10 million light year radius we can see here. We can see our Milky Way galaxies hanging out here. We have some weird dwarf irregular galaxies, some satellite galaxies that we've been able to pull in. And then over here, we can see another kind of brighter smudge. That guy's called M31, also known as the Andromeda galaxy, which is about 2.5 million light years away from us. Now, Andromeda's neat because she is coming towards us at like 80 miles a second. And we are set to collide with Andromeda in about in about like 5 billion years. So conveniently around the same time our sun is set to explode. So that'll be like a fun little party in the solar system. Now, how galaxy collisions work. This was actually, this animation was made with a supercomputer, combining math and actual images, Hubble images of galaxy collisions. When the Milky Way and Andromeda start bumping into each other, it's not going to be like stars hitting stars, planets hitting planets. It's going to be our two supermassive black holes are going to try to become a binary system. So we're going to have a lot of weird gravitational waves. Stuff's going to be thrown out of galaxies. We're going to have rogue planets and rogue stars all over the place. And this whole, collision, it's not just going to happen in one day. It's going to, over the course of hundreds of millions of years. And we're going to form either Milkdromeda or Andromeda Way. They haven't really come up with like a set name for it yet. But yeah, that'll be like a fun little party. So we got a bunch of stuff that could a bunch of outcomes that'll be going on as these galaxies collide. Yeah, let's go ahead and do that. Maybe there we go. Come on, not bad. Am I dumb? Yes, there we go. As we zoom out further, so we were 10 million light years away looking at Milky Way and Andromeda. Now we're 50 million light years out, and we see what look like these little neurons. This is visible light, or light that we've been able to see and map in a 50 million light year diameter. And so we see, there's these clusters of galaxies. All of this light are individual galaxies. There's these clusters of galaxies. We believe galaxies are clustered together through mutual gravity. And then there's the elusive dark matter and dark energy. When it comes to dark matter and dark energy, all we know is dark matter is matter that's dark. We can't see it, but we think it's there. Dark energy, it's the same thing, where it's energy, maybe some sort of heat or something, but we can't map it. We can't see it. So, we see, oh, no, not that one. we see, you know, these superclusters. We're in the Virgo supercluster. We're hanging out in there. This is a 500 million light year diameter, 500 million light years in diameter. So we have all these different clusters of galaxies. Every single little speck in here are, you know, dozens of galaxies. We're right about there. Yeah, we see these like voids as well. And, you know, they're not voids because there's nothing there. There's voids because we can't see anything there yet, which is like really neat to think about. And, you know, as we zoom further and further away, we've got our Milky Way, we've got Andromeda. And as we zoom further away from these galaxies, now every speck of light that we're seeing is a single galaxy. So we see all of these dots of billions or trillions of stars clustered together. We see individual clusters, all of these dozens and dozens, and then hundreds and thousands of clusters of galaxies in the known universe, which is crazy to think about. One thing I'd like to mention here is, you know, in our own, you know, galaxy, we have over 400 billion stars, and we believe that there are more planets than there are stars in our galaxy, which means there are over 800 billion planets. And we think that's how it is with all galaxies like ours. So in the universe, there should be more planets than stars, and people still think that there aren't aliens. And I'm not just saying that to be funny, like genuinely, like the scientists believe that we can't be the only form of intelligent life. Like, come on. So if we zoom 10 billion light years out now, okay, the universe is 14 billion years old. Over here, we see this weird thing. It looks like a keyboard smash. Those are called quasars. They stand for quasi-stellar radio sources. Quasars are some of the oldest things in the known universe. So they're interesting because quasars, when we take pictures of these guys, these are actually baby galaxies, which is weird. It's kind of like, because we're looking 10 billion years into the past. So this is kind of like looking at baby pictures of your grandparents. So like they're really old now, but in this picture or in this view, they're really young. The Hubble Ultra Deep Field is one of my favorite images ever taken, because we took the Hubble and, you know, with like normal telescopes or telescopes on Earth, we couldn't really see any galaxies in this little tiny piece of sky right next to Ursa Major, right next to the Big Dipper, this area of sky that's the size of a dime held 75 feet away from you. And we took the Hubble and we're like, let's just point them there for 11 days and see what happens. And we found over 40,000 galaxies in all different, you know, stages of their lives, galaxies colliding, galaxies that we have no idea what's going on. 11-day exposure. The Hubble stared at this spot in the sky, took pictures, and compiled 11 days worth of exposure. And it's just crazy to think about all of the stuff that we have no idea what's going on. You know, beyond that, those 10 billion light years, beyond that, we hit the oldest heat in the universe, the cosmic microwave background. This is in the radio wavelength. So this is like the first heat ever formed in the universe, or what we believe is the first heat. You know, this stuff isn't only found 14 billion light years away or 13.5 billion. It's found all over the place when we look at radio waves. So, you know, when it comes to like the start of everything, there was nothing, and then there was a particle, and then there was something, and then there was two particles, and then these guys smushed together and they created more particles, and then bam, gravity's a thing, and bam, mass is a thing, and energy and light's a thing. And that's all because of the cosmic microwave background. So seeing the CMB is like proving the proof of the Big Bang theory. Now beyond that cosmic microwave background, we have no idea. We can't see the Big Bang happening. We believe, or there's the James Webb Space Telescope. That guy's the successor to the Hubble. Some scientists believe that with the James Webb, we will see light from before the Big Bang, if there is any, which would be phenomenal, you know. And then we get into cosmology and theory, and that stuff gives me a headache. But We think there was the Big Bang, but if the James Webb could like confirm it for us. And you know, to sort of close out here, the talking about how big everything is and how far away everything is and how long everything lasts, it's normal to like feel kind of small, feel kind of itty bitty. But I like to point out that all of these beautiful, phenomenal, astounding objects, all these nebulae, all these galaxies, these stars, these stellar deaths, these stellar births, not to get all Carl Sagan on you, but, or yeah, to get all Carl Sagan on you, like you are genuinely made from all of this stuff. The oxygen that we breathe, the carbon in our body, like we are made of this stuff. So next time you look up in the sky, you know, and see all these bright stars, rather than feeling small, I'd want you to feel big because you are made of those stars. So thank you guys for hanging out with me. And that just about concludes my Stars and Galaxies talk. So if there do happen to be any questions, I can totally answer them. I'll be hanging out. So
thanks so much, Ariel, for the presentation. Please, if you have questions, do submit them in the chat, but we are also aware it's almost 8 o'clock, so we'll stick around a little bit longer for those that do have questions and answer. But for those of you that have to get going, I just want to say a quick thank you to everyone that attended this evening, and we'll get started on some of the questions. So our first question is it possible when you're looking at something that's light years away and therefore many years in the past, that if you could see a current picture of the same thing?
So to get like a current picture, if you're looking at something that's light years away, it would look completely different now. And there's no real way for us to like get a current picture of those objects unless like we somehow like throw a space telescope faster than light speed towards the galaxy to somehow go back in time. We get into broken physics at that point in time. But basically, there's no way to get current images of these galaxies that we're looking at now. I believe that was a question, right? I believe so.
Yes, thank you. And then someone says, first they say, wonderful presentation. Want to make sure you hear all of the great feedback that you're getting in the Q&A as well. But they asked, how is the picture of the Milky Way and some of the other galaxies taken?
Yeah, so the picture of the Milky Way was actually created, it was created by a professor at the University of Wisconsin-Madison. So it was made from, it was like a computer generated image. Like I was kind of mentioning, like, you know, we can't zoom 100,000 light years out of our galaxy to take a little selfie. So we just, through math, we're able to like try to predict how this galaxy should look. So yeah, that was a computer generated image of the Milky Way. We're pretty sure it's a spiral. Yeah.
And the next question is, can you please expand on the light before the Big Bang and how can we see light before that singularity?
So the James Webb Space Telescope, that guy will, I believe he'll specialize in seeing an infrared light or heat-based light. So if there was any heat or light from like before that Big Bang, the James Webb hypothetically could detect something like that. So yeah, the James Webb should be launched. It's been pushed back for forever, for like years, but it should be launched actually in October of this year, Halloween of this year. So that'll be fun. Let's hope it doesn't get stolen. There's actually, I saw an article the other day that was like, NASA's worried about space pirates. And I was like, no way. And I clicked it and it was like, oh, it's just like being transported by boat. It would really not be awesome if it got stolen. Like, so yeah.
Awesome. Our next question is, what is the concept of multi-universes? Will our universe continue expanding without stopping?
So there's like, I've heard of like multi-universe theories before. there's like definitely like there's a bunch of galaxies, and all these galaxies are drifting apart from each other because of the expansion of the universe. And that actually, the discovery of redshift in galaxies, that these galaxies are moving apart from each other, what came from Lowell Observatory. We were working with Hubble, Mr. Hubble, Edwin Hubble, and we figured that out together. Now, oh man, what was the question again? It disappeared. Oh wait, here it is. Sorry. Light. Oh, multiverse. Yeah, our universe continue expanding without stopping. That that concept. There's like three main like endings to the universe. There's like the big crunch, the big rip, or the big freeze. So it's basically like dark energy is what's making our universe expand. If dark energy production stays constant, all these galaxies continue drifting apart from each other. If all of a sudden that dark energy increases exponentially, they drift apart way too fast. Galaxies rip apart, the big rip. And then if all of a sudden that dark energy like goes completely south, or like completely opposite of exponential increase, we'll get the big crunch, where all of this stuff, it's like a opposite Big Bang. All these things will collapse back in on themselves. So we have no idea what's going to happen. So that there's like, the three kind of like endings to the universe. It may continue expanding without stopping. That's like the most common like belief. Or it could expand way too fast, or it could just stop expanding and flip on back around. Yeah.
And thanks, Ariel. So the next question is, what can we do to defeat urban light pollution in our neighborhoods to better see the night sky?
Yeah, so Flagstaff is actually the world's first international dark sky city. And what we do is we have like a dark sky coalition, and it's like all of the lights in Flagstaff. If you've been here before, if you're coming to Lowell after this, that'd be fun. All the lights, the street lights, are like really yellow. They're low pressure sodium lights, and they have these little hats on them to where all of that light shines down. And that makes it to where we get little to no light pollution at all from the city. So when it comes to like defeating urban light pollution in the neighborhoods, it'd be like talking to the people who run the city. Be like, hey, I'd love to be able to see the Milky Way in the middle of the city. I believe Flagstaff actually, we like tax businesses who don't follow the like low light, the dark sky city like mandates. So even like in like my neighborhood, I have no street lights. Downtown there are street lights, but they're like dim. And then like way out in like Kachina Village, there are no street lights. You're like driving in the middle of the forest, and it's terrifying, but it's cool because when you're like in the middle of downtown, in the middle of the city, you can see our own galaxy with your naked eye. So I believe dark sky cities are wonderful, but it is very difficult the more populated the city is. So it definitely depends on like what like cities there are, because you could have like low light neighborhoods, but that wouldn't necessarily make like completely erase light pollution wherever you're trying to be, like in your neighborhood or in your city.
Thank you. And just a couple more questions, but the next one is, how do you determine the size and distance of a star from the Earth?
Yeah, okay, so there's a bunch of different ways that astronomers do stuff like this. One of the there's like a certain type of supernova that astronomers use as like a, oh gosh, what are they called? Candles. So like if we can look at this thing in the sky and be like, oh, that's a type, man, I want to say type A or type 2 supernova. I couldn't tell you right now, but a certain type of supernova, okay, it should be this bright. A standard candle, I think that's what it's called, standard candle. And if we see this supernova, we know it's this kind of supernova, but it's only this bright. Just through luminosity alone, we can figure out how far away that thing is. With finding out distances of stuff from Earth, another really common like method that astronomers use is called parallax, where it's kind of like if you took your finger and blinked one eye and blinked the other one, it kind of looks like your finger like pops on different, looks like your finger moves. It's like we do that, but in space. So we'll look at a star, in a certain point in its orbit or point in our orbit. We'll look at the location of it, and then on the other side of Earth, we'll look at it again and see if there's any parallax with that star. So through some really complicated space-age geometry, we can figure out distances of stars. So parallax, just like luminosities of stars, can tell us distances. It's weird to think about, but there's a bunch of different ways that astronomers can figure out sizes and distances.
And then, do we have any evidence of dark matter present in our own galaxy, our solar system?
Yeah. So in our solar system, not hard evidence, but in our galaxy, it's actually very interesting. There was research done by an astronomer named Vera Rubin, and she was looking at galaxy movement. And, we have like the core of our galaxy and, our supermassive black holes in the core. And as you get further and further away from that black hole, since there's just like less mass, less stuff, that movement shouldn't be as fast as the core of the galaxy. So it isn't, which is why we have those spiral arms, but it should be even slower, which would just like completely destroy galaxies only a couple billion years after they were formed. But we still see these spiral galaxies that we don't see any mass in the outskirts of the galaxies, but they're staying like a proper shape, like a proper spiral shape. So that led astronomers to believe like, okay, maybe there's mass that's keeping the galaxy together that we literally cannot see in any wavelength of light that we know of. So that introduced the concept of dark matter. It was primarily Vera Rubin's research on galactic movement. So galaxy cores spin faster, the outside spins almost just as fast, and that doesn't make any sense unless there was some mass there. If there wasn't, then physics is broken. So to follow the laws of physics, there had to be something there. So we called it dark matter. So it's very elusive, very funky to think about, but yeah, dark matter.
And then our last question for this evening is just a little bit more about Lowell Observatory and how our attendees can visit, or when the best time is to visit.
Yeah. So I believe we just began like phase 2B or something. What that means is like, you guys can come in. It'll be, if you actually check out our website, like Lowell. Oh my God, I think it's lowellobservatory.edu. Google Lowell Observatory. Our website's on Google. I think it's lowellobservatory.edu or lowell.edu. It's lowell.edu. That's what it is. But check out lowell.edu and you can actually reserve spots. So we don't do like walk-in guests right now. We're still limiting to like reservation-based like get-togethers. But if you come during the day, we have day tours, which are they're like 2 hours long. You get to see our historic Clark telescope, which helped discover that the universe was constantly expanding. It studied Mars. It mapped the moon for the Apollo programs. You can see the blink comparator that Clyde Tombaugh used to discover Pluto, as well as the Pluto Discovery Telescope, and do solar viewing during the day. So we can actually look at the sun safely. If you come at night, we do a lot more. We do a little more. So we do historic tours as well. So we, visit our historic telescope domes, but also we'll do nighttime viewing with our Giovale Open Deck Observatory. So that is one of our newer facilities. We have 6 state-of-the-art telescopes that are built specifically for people to view through, for guests to come and look at stuff. And actually, Ooh, I don't know if the weather's awesome tonight, but on Tuesdays we do interactive stargazing on our YouTube channel, where we, for free, we live stream stuff that we look at, and you can like type in the chat and be like, "Hey, I want to look at this thing," and then we'll take our telescopes and look at that thing and live stream it for you. So I would actually maybe chat. I can. Our social media usually updates that. I don't know how the weather is right now. I can't tell how the weather is right now, but anyways, yeah, we are open to the public. You just have to do a reservation. You have to make reservations online. Yeah, would highly recommend. I have a blast. Everyone at Lowell has a blast, and all the guests have a blast. We also have like a kids tour too, where we do science demos, like throw liquid nitrogen around.
Well, thank you so much, Ariel, and thank you to all of you who attended this evening. It was such a joy to have you present with us, and hopefully we'll see you at another DePaul alumni event. If you haven't already, check out our calendar on site. I hope you all have a great rest of your evening. Bye.